All right, so this is what I asked you guys to discuss in your group, and I'm just going to put this up here real quick. So I'm going to assume someone out there can answer this. What is the probability of N, and what is the probability of S? You can just write those in on the screen. All right, there we go. We got that one. What is the probability of N? Okay. I like it. I like it. 0.95. Okay, so just to put this in context for people who didn't read through it and still are a little bit lost, we're talking about probability of S is the probability of getting a statistically significant result, and the probability of N is the probability of not getting a statistically significant result. So those are two mutually exclusive and exhaustive outcomes of this. So they're going to be complements of each other. So there we go. Now, not only that, but we are also working under the assumption that the null hypothesis is true. So when the null hypothesis is true, there's going to still be a 5% chance of getting a statistically significant result, or whatever our alpha level is. And here it's 0.05. So remember, just by random chance, that might happen. So now what we're doing is we have this probability tree, a tree diagram going on, and we want to figure out what is the overall error. If we perform multiple t-tests, we could get a statistically significant result, or we could not get one, assuming the null hypothesis is true. We get these probabilities. So anyways, my point and the point of this problem is, if we perform two of these in a row, then what is the overall family error rate? And this is something I kind of want you to be aware of. This is something that an investigative task might do, where it gives you a new idea. We've never talked about family error rate, okay? But that's not a problem, because it's really just taking the idea of tree diagrams and conditional probability and putting it into action here in terms of hypothesis testing. So I'm going to put some blanks right here, and I'm going to see if you guys can fill in what are the different probabilities for going down each branch of this diagram. Okay, we got our initial 0.05 and 0.95. And then what's the probability for that? Okay, I see where you're going with it. And that is, I'm going to jump in right here before people start filling in the rest of this. This is what we get to eventually, but actually, and so that's a good answer. But I am going to, well, I can't erase it, but that's okay. I could erase it on the screen. We still have a 0.95 probability of getting a not statistically significant result, because we're saying for the next test, what's the probability? The probabilities are the same. We're going to jump to that next calculation that you just did, Zach, at the end. So I'll just fill in the rest of this, nothing too complicated. Anytime we get no statistically significant result, that's a 95% probability versus a 5% for getting a statistically significant result. So now how we end this is we say the probability of getting not a statistically significant result and not a statistically significant result, that's where we're going to do what you just did, Zach. So that's going to be these two probabilities multiplied together. Those are independent events. So we can certainly just multiply them. We don't have to do any corrections for conditional. Well, actually we did. This is conditional probability. I should add that in. But it's already accounted for right here. So the conditional probability for all this is going to be 0.9025. That's just the 95 times the 95. All right. Now, this is going to be the probability of not getting a statistically significant result and then getting one. So that's going to be 0.95 times 0.05. So it's worth pointing out that this probability is technically the probability of not getting a statistically significant result, given that you didn't get a statistically significant result. So that's where the conditional probability is. But it doesn't change because they're still independent. All right. So now we've got, this is going to be 0.0475. Now this is going to be the probability of first getting a statistically significant result than not, which is the same calculation. And oops, hope I'm not going too fast and confusing anyone. But notice that this is still 0.05 times 0.95. So the calculation hasn't changed for those two. And lastly, we've got the probability of getting two statistically significant results in a row. When there's only a 5% chance of that happening, is going to be 0.05 times 0.05, which is 0.0025. So this represents the entire probability distribution of these two events. And we know we did it right if these all add up to 1, and they do. And now what we want to consider is anytime we get a statistically significant result when we should not have is an error. Okay, so that's a type 1 error in this case. So when we do two tests like this, we end up with 3 different outcomes that result in errors. And only one outcome that's what we want. So for one test, we had a 5% chance of getting a type 1 error. Now our type 1 error probability has gone up. All right, and we can do this 2 different ways. We can just add these probabilities together, and then that would be 0.975, or sorry, 0.0975. Or we could do 1 minus the only outcome that's good for us. And we get the same answer regardless of how we do it. And we can see now that our family error rate is nearly 10%. It's nearly doubled. Okay, now if we added one more test onto this, and we could do all kinds of conditional probability one more time, but that's just extra complication and we won't worry about it. All right, if there are questions on this, then you guys we can come back to this later. On this one, I do not want to run through the whole thing. This is the entire FRQ. And so hopefully you guys did this and you knew what you were supposed to be doing. We're looking at chi-square tests. So the first thing we need to do is add totals here. So what is the total number of people who liked regular versus diet versus no preference soda? We should have 200 total because that's my row total right here. So anyways, if I add across for regular soda, it looks like 81 right there. If I add across for diet soda, that's 81. And if I add across for no preference, that's 38. So when I add these up in the column, that does add up to 200, so we're good to go. So at this point, all we need to do is set up our matrix in our calculator for the observed counts, and then we can do our expected counts. And I'm not going to go through all these. Actually, I might go through all of them because it's pretty straightforward. Notice one thing really convenient about this is that we have the same sample. We have the same amount for East and West Coast. And when that happens, we have this really nice thing where we're going to take this value and just split it in half. So what we're essentially doing is 81 times 100 divided by 200. That's your row total times your column total divided by the table total. But notice that this just reduces down to 81 times 1/2. When you have the same number in each column, it works out really nicely where we can just divide it by 2. So that's 40.5. This is 40.5. This is going to be 40.5, and so on. So we can come up with our answers pretty quickly here, 19 and 19. So those are the expected counts. We can now go into our calculator and run this, and pretty straightforward. Unit 12, Inference for Linear Regression. This is our most recent content that we introduced, so hopefully it's fresher on your mind and you are not gonna have to dig too deep to bring this back up. Inference about the slope of a regression line. Okay, that's what this was all about. And but the key thing, the reason I wrote that is that we're talking about the slope of a regression line. That's the only thing we're doing inference on right here. If it's a hypothesis test, we're always starting with the assumption that there is no association, that's the null, and we're just going to have an alternative that says something different. Confidence intervals are going to estimate the true slope. And this is just a point it's worth repeating. Hypothesis testing is just to say, is there a statistically significant difference between these two? But we don't know what the true value is. We could turn around and do a confidence interval to say, okay, there is a statistically significant difference. What might the true value be? And so remember, your slope represents things in context. So for every change in your explanatory variable, you're going to get some kind of change in your response variable. And the context there matters. So your confidence interval can estimate, oh, for every extra inch of height we add, we're going to gain X amount of pounds, or Y amount of pounds, and that is what our prediction would be. So keep in mind how to use that in context. The specific formula is given right here. First of all, I made a mistake on this, but I'll get to that mistake in a second. So this is your standard error calculation. And this is your, that's the important thing. But I went ahead and wrote it out only this way for the confidence interval. But one thing that we know is that frequently we do not have all these values. And the value we usually don't have is this standard deviation of the X values. Sometimes they provide it, sometimes they don't, but they always provide. And this is where I made a mistake. It's not S sub E. This is S sub E. This should just be SE for standard error. They always will have a printout with a standard error. So frequently we can ignore this, except maybe to show it in our work. But we don't actually need to plug values in a lot of the time. So pretty straightforward. And mathematically, this is probably the easiest stuff that we do. The conditions, this is a little different. We've got linear, so linear, independent, normal, equal variance, and random. And one other thing I didn't put in the bullet points is that we also dealt with when we had re-expressed linear regression lines that might have had log or square roots and stuff like that. And so the very first problem we have here, we'll deal with that. So the natural log, this is the re-expressed linear regression line. X is the fuel efficiency, Y hat is the predicted carbon dioxide emissions. And we want to predict the carbon dioxide emissions for 18 miles per gallon. Sorry, mixing my units up. 18 miles per gallon. So this is a very straightforward natural log of Y hat equals 8 minus 0.055 times 18. We can plug this in. I already did this math earlier, so I know it's going to be 7.1 right here. And just the key thing to remember is that when you have natural log or just log base 10, then you're going to need to do the opposite. The opposite of this is going to be e to the power of natural log of Y hat. So e to the 7.1. If it was log, then it would be 10 to the power of. These cancel out, Y hat equals, and we can figure that out. The actual answer is this right here. Okay. In this one, we are trying to figure out, and notice right here that we are estimating the mean change in concentration for each 0.1% salinity in lake water. So this is talking about concentration of animal life. And we got a sample from 30 lakes, all well and good. So what test should we use if we want to figure out or estimate the mean change? Well, when we are estimating a specific value, it's not a test, it's an interval, because interval will tell us that. It's going to be a rate here of expected amount of concentration added or lost per 0.1% salinity. So that we're talking about slope, and this is it right here. Next one, we are looking at the relationship between sample size and the width of a confidence interval. So they tell us what the confidence interval is right here, but they don't tell us too much more. We just notice 15 data values, and then that confidence interval. The researcher says the interval would have been wider with different sample size. That is true, and let's remember that our margin of error is pretty much exclusively dependent on 3 factors, which is going to be all related to the standard error. So we've got n minus 1. So this is the standard error calculation. And this is the standard, or the standard deviation of our residuals. So if your data is more tightly packed around the regression line, that's going to decrease the width. So the smaller your residual standard deviation is, the better. If this was scattered more widely, then our margin of error goes up. The standard deviation of your X values, we want to make that bigger. So as this goes up, so we want our data to spread a wide amount. If we only had data that covered this much, that's not as good for our regression line. Just keep in mind, we want to have a bigger trend of values, longer kind of span of the data to work with. And most importantly for this problem, they're asking about sample size. This is inversely related. So as sample size goes up, the width decreases. And we've seen this over and over again. So on the flip side, as your sample size goes down, your width is going to increase. And the researcher is saying that the interval would have been wider. Well, the only way it gets wider, talking about sample size, is if the sample size goes down. So if we started with 15, then all of these values right here, 8, 12, 14, and 10 are less than 15. So yes, that would have made the interval wider, but 16 is actually bigger. It would have become narrower in that case. This is one that was not seen by most people on the test. And this is the residual plot for a specific scatter plot. And what is violated as far as your conditions for inference? What is being violated right here?
It doesn't have equal variance because the residual line is at 0, I think. And so they're all different distances away from the residual line.
That is likely true. I think that's fair. It's almost a fair answer to this one, but there's one that's more obvious than that. Do we see anything else that jumps out?
It's not linear.
It's not linear. Now, I don't think you're wrong by saying the equal variance isn't met, but typically that's something else. That's whenever we see a trend that looks like this. But here we're also seeing very clearly that there is a nonlinear trend going on. This can happen. This can show up in your residual plot that doesn't show up. Sorry, clear that. It doesn't show up in the scatter plot. So it is entirely possible that the scatter plot could look like this. All right. And the nonlinear trend bit only appears whenever you look at the residual. Or it is very clearly there when you look at the residual. So it's the linear condition right here that's being violated. Okay, now we're looking at what is the correct hypothesis or the correct hypotheses for this test. A doctor is recording miles of jogging each week versus resting heart rate for 40 patients. And we know, just before we even look at anything else, that the null hypothesis is always that beta, which is our population slope, is going to be 0. This is always the null hypothesis. So I can rule these two out. Oops, not that one. This one. Now the other one is a little bit trickier. So because it doesn't say specifically what direction we think this slope should be going, the best answer is this one right here. The alternative would just be that beta doesn't equal 0. This is one that's a little bit tricky because you, having some prior knowledge, might have an idea about what the answer should be. And what you might think is that as miles goes up, jogging miles goes up, your heart rate will go down, which would be a negative slope. So we might expect that our population slope would be less than 0. That is a fair idea, but because it doesn't ask us specifically to test that it's going to be a negative slope, the best answer is this one. So anyone who did answer this on the test got half credit, but there you go. And I believe, yeah, this is the last one we're looking at, guys. So here we've got a baseball enthusiast carrying out a simple linear regression to investigate whether there's a linear relationship between the number of runs scored by a player and the number of times a player was intentionally walked. Computer output from the regression analysis is given. And this is basically talking about our hypotheses, but really in the end it says, what is the appropriate test statistic for the test? What is the number for the test statistic? And this is determined by, remember, it's your slope minus beta over s divided by s sub x divided by the square root of n minus 1. And like I said at the beginning, this value we don't even need to worry about. I'm going to replace this with b minus beta over just the standard error, because they didn't tell me the standard deviation of the x values, so I can't use that. And that luckily makes our life a lot easier. This is found in the printout, so we don't care about the intercept. I want to remind you of that. So the only values we care about, the estimate right here is our b, that's our slope. And this is going to represent our standard error. And it's very conveniently labeled as standard error right there at the top. So all I need to do is plug in 0.6 minus beta. Well, let me come back to that. Divided by 0.051. And because our null hypothesis is always that beta is equal to 0, this becomes 0 right here. It's just 0.6 divided by 0.051. And it's a very straightforward calculation. Doesn't get any easier than that. Calculator somewhere. I think the answer is 11.76. So let's go with that. Why not? All right. So that is all of the Unit 12 review. Heavy on concepts, very light on actual calculations you need to do. So there's an FRQ related to it. You can, this requires you to set up scatter plots and some other things. So this one's going to be a little bit in depth, but not too bad. Finish that practice test tonight. In fact, finish all of the work that you need to do to get turned in, because it needs to be turned in by tomorrow night. If you don't have any questions on that, actually, before I release you, I wanted to remind you, tomorrow we're just going to be grading the practice test. And essentially what's going to happen is if you have questions, you can stick around and we can go over, there's 40 questions on the practice test. You can just pick whatever questions you want to go over. But if you do not have any questions on it, then you can just come check your test. Have a wonderful day at that point. So now, at this point, if you don't have any further questions for me, you can have a great day. I will see you tomorrow. But if you do have questions, stick around. So have a great day. I'll see you tomorrow.